In mathematics, more specifically in statistics, Markov chain Monte Carlo methods are a class of algorithms for sampling from a probability distribution based on constructing a Markov chain that has the desired distribution as its equilibrium distribution. The state of the chain after a number of steps is then used as a sample of the desired distribution. The quality of the sample improves as a function of the number of steps. Random walk Monte Carlo methods make up a large subclass of MCMC methods. Application domains. MCMC methods are primarily used for calculating numerical approximations of multi-dimensional integrals, for example in Bayesian statistics, computational physics, computational biology and computational linguistics. They are also used for generating samples that gradually populate the rare failure region in rare event sampling. Classification, random walk Monte Carlo methods. Multi-dimensional integrals. When an MCMC method is used for approximating a multi-dimensional integral, an ensemble of walkers move around randomly. At each point where a walker steps, the integram value at that point is counted towards the integral. The walker then may make a number of tentative steps around the area, looking for a place with a reasonably high contribution to the integral to move into next. Random walk Monte Carlo methods are a kind of random simulation or Monte Carlo method. However, whereas the random samples of the integrand used in a conventional Monte Carlo integration are statistically independent, those used in MCMC methods are correlated. A Markov chain is constructed in such a way as to have the integrand as its equilibrium distribution. Examples of random walk Monte Carlo methods include the following: Metropolitan-Euro-Hastings algorithm. This method generates a random walk using a proposal density and a method for rejecting some of the proposed moves. Gibbs sampling. This method requires all the conditional distributions of the target distribution to be sampled exactly. It is popular partly because it does not require any tuning. Slice sampling. This method depends on the principle that one can sample from a distribution by sampling uniformly from the region under the plot of its density function. It alternates uniform sampling in the vertical direction with uniform sampling from the horizontal slice defined by the current vertical position. Multiple try metropolis. This method is a variation of the Metropolitan-Euro-Hastings algorithm that allows multiple trials at each point. By making it possible to take larger steps at each iteration, it helps address the curse of dimensionality. Reversible jump. This method is a variant of the Metropolitan-Euro-Hastings algorithm that allows proposals that change the dimensionality of the space. MCMC methods that change dimensionality have long been used in statistical physics applications, where for some problems a distribution that is a Gram-canonical ensemble is used. But the reversible jump variant is useful when doing MCMC or Gibbs sampling over non-parametric Bayesian models such as those involving the Dirichlet process or Chinese restaurant process, where the number of mixing components is automatically inferred from the data. Other MCMC methods, reducing correlation. More sophisticated methods use various ways of reducing the correlation between successive samples. These algorithms may be harder to implement, but they usually exhibit faster convergence. Examples of non-random walk MCMC methods include the following: hybrid Monte Carlo tries to avoid random walk behavior by introducing an auxiliary momentum vector and implementing Hamiltonian dynamics, so the potential energy function is the target density. The momentum samples are discarded after sampling. The end result of hybrid Monte Carlo is that proposals move across the sample space in larger steps. They are therefore less correlated and converge to the target distribution more rapidly. Some variations on slice sampling also avoid random walks. Langevin MCMC and other methods that rely on the gradient of the log posterior avoid random walks by making proposals that are more likely to be in the direction of higher probability density. Convergence. Usually it is not hard to construct a Markov chain with the desired properties. The more difficult problem is to determine how many steps are needed to converge to the stationary distribution within an acceptable error. A good chain will have rapid mixing. The stationary distribution is reached quickly starting from an arbitrary position. Typically, MCMC sampling can only approximate the target distribution, as there is always some residual effect of the starting position. More sophisticated MCMC-based algorithms such as coupling from the past can produce exact samples, at the cost of additional computation and an unbounded running time. Many random walk Monte Carlo methods move around the equilibrium distribution in relatively small steps, with no tendency for the steps to proceed in the same direction. These methods are easy to implement and analyze, but unfortunately it can take a long time for the walker to explore all of the space. The walker will often double back and cover ground already covered. See also, Bayesian inference, coupling from the past, Gibbs sampling, hybrid Monte Carlo, Metropolis Euro-Hastings algorithm, multiple tri-metropolis, particle filter, reversible jump, slice sampling, notes. References. External links, MCMC sampling and other methods in a basic overview, by Alexander Mantsaris, visual demonstration of MCMC sampling methods, by Led Breyer example of MCMC sampling, by Ziyuan Wang, MCL, a cluster algorithm for graphs, by Sturge van Dungen, PIMC, Python module implementing Bayesian statistical models and fitting algorithms, including Markov chain Monte Carlo.